Welcome back, chat. 500 or to the first person to comment below. I don't know how it works. Is it comments? Shout-outs? I'm going to have to watch something on Twitch, but I really don't want to. All right, here we go. We are talking higher order polynomials today. Now, we've never used the word order of a polynomial, I don't think. Now, when we're talking about these, I'll tell you quadratics. What's their degree? What do you think their order might be then? 2. Second order polynomials or second degree polynomials. Now, as we get going with larger orders, there's a couple little statements that I just want to kind of start in with. And all of it will fit in within this nice kind of focus where we are first going to talk about graphs of polynomials. Now, we have dealt with quadratics and we have dealt with linear functions, which are kind of uninteresting polynomials. But there's two big statements that we're going to start with as we're talking about graphs of polynomials. Just so you know, I'm shorthanding this before, like in my notes it says graphs of polynomial functions, but we're all talking about polynomials nonetheless. Okay, first thing, two big topics, and I'm just going to say note. Polynomials are what we call smooth curves. Okay. This is one of the few situations where I struggle with like a legitimate mathematical definition because this is almost an aesthetic that we're looking at. You think you could tell me the difference between a smooth curve and a not smooth curve? Just your gut, you think you could? We'll see, because there's not a whole lot of confidence there. I'm not even going to put an axis. Those are essentially the same shape. One of them smooth. Top or bottom is smooth. We can all agree, I think, when we see something that's smooth like this, no abrupt corners. There's some calculus language that would help clarify this idea. Don't make absolute value looking graphs when you're doing polynomials. Okay. Now, what the weird situation is, that is a polynomial. It's a linear function. It's not a curve, but it's smooth, I guess. Maybe. I don't know. There's no curve. Like, I don't know. Is a line smooth? Maybe. I don't know. Until it turns, I guess so. Okay. Beyond that, polynomials will always be smooth curves. We were going to try very hard not to make it look pointy. Second thing, they are continuous. Polys are continuous. Now, there is really formal definition that we can make here, but I'm going to just make a single statement that we're all going to open our ears wide open here in just a second. Continuous. And my N's and U's look alike, so I'm sorry about that. You need to be able to pick up your pencil and draw the whole graph with the understanding that we can't really draw to infinity without ever picking it up. So I can't jump like this. Like a piecewise function that comes in and then jumps to another value. You have to be able to do it without picking up your pencil. There are some small exceptions where we'll see issues with this, but 99.9% of the time we're just going to say they're always smooth curves and they're always continuous. Okay. Beyond that, as we start looking at these, the easiest type of polynomial that you'll deal with is what's known as a power function. X to the whatever. It doesn't matter. You can actually come in if you'd like. Okay. So if we look at x to the third, this is apparent, right? And you guys have seen this. Now, as we go through here, power functions, and I should have changed color. Power functions are the simplest type. All of your parents, x to the 1, x to the 2, 3, 4, 5, don't care the number. Those are all just power functions, what they're referred to. We're going to go more in depth. As we deal with these graphs, essentially, I'm going to make the claim we only need like 2 or 3 pieces of information to get at least a rough idea of what's going on. Can you tell me any important components or characteristics of a graph that you might think of? So I'm going to sketch a graph in white, and you guys are going to help me out here. There's probably a polynomial that looks something like this. Like, I don't know what it is, but I bet it exists. Do you guys agree with that? Can you tell me, and talk with your neighbors for like 60 seconds, I want you to find me all the important parts of this graph and what you consider important. And it might be, it might not be in my mind, but I don't care about our difference of opinion. What is the important information you would need to graph something like this? I'm going to give you a second. Give me something important, JV. Hey, these guys. Okay, I agree with you. Whoa. Those in that one? Okay, anything else? Oh, I love it. We need to know where it's maximum, where it's minimum, because that tells us where it's going to wind up turning. Okay? Anything else that's important? Holy end behavior. I just need this. Now, what winds up happening is if I give you just that information, if I say, oh, here's what it does at the end, here's its roots, here's the mins and maxes, you could sketch this graph pretty stinking close to what it is. We might have a little bit different of like how bendy is it in certain places, but the same basic idea would show up. I guarantee it. Turns out that if we can all agree, did anybody come up with a different one? Now there's some other words that do show up in here, but you guys, if you've hit all those, I agree with you wholeheartedly. All right, so we're going to be looking at how does one go about actually graphing these things, and we're going to have like 3 pretty small sections today, just so you're aware. Polynomials are smooth, they're continuous. Everybody cool with that? Okay, have you guys ever done the math dance? Oh, bummer. Would you like to learn the math dance? Cool, it's really easy. When we're looking at these, any polynomial, and just as a reminder, these things always look like that super ugly a sub n x to the n plus a sub n minus 1 x to the n minus 1, so forth and so on. We are first going to use this to our advantage, the leading coefficient test. If you want to shorthand for LC, I'm good with it. Coefficient. This looks like it's spelled wrong, but it feels right. Test. Okay. Now, to start off, all that we care about is the following statement. Given, and I'm not even going to write the whole polynomial, I'm only going to write the very first part. Given some function f of x equals a sub n x to the n plus a bunch of stuff that I don't care about. There could be a ton more information there, or there could be no more information there. If you give me a polynomial that has a leading coefficient and you can see the degree or the order of this polynomial, you get a ton of information from it. So we're going to make a little table, and I want you guys, if you don't have one, grab your calculator, or one person in your group grab a calculator, and I want you to play around with stuff. Okay, the table that I want you guys to have is going to be the following. We get a function, and I should have just written it here. We're going to make a little table. We're dealing with functions that look like this. A sub n x to the n plus a bunch of stuff. And I'm sorry it's redundant. Now, if I asked you to identify the leading coefficient of this function, can you? So let me rephrase, because I guarantee you can. With your neighbors, tell me, for this particular function, what's its leading coefficient? So this is really loud today, I'm sorry. So it could be 1. Doesn't have to be. Did somebody quietly murmur a sub n? Okay, louder murmurs next time. Now, what's the degree of this function? N. A sub n is the leading coefficient, and n is the degree. Now, I'm going to claim there's only like 2 real possibilities. Give me an example of what n could be to still be a polynomial. Shout out a number. Give me any number that n could be. 3 works perfectly. Charles, give me another number that n could be. So in white, I'm going to write these. I heard 3 and I heard 2. Give me another one, JV. 4. Give me another one, Riley. 6. Give me another one, Angel. Could be 5. And then could it be 51? It'd be weird, but it could be. I've separated these in a particular way. If you give me a polynomial function and we're talking about its degree, there's only 2 options. It's either in this side of the table or this side. How did I separate these numbers? One more time, I'm sorry. Even and odd, right? So, if we have first opportunity, n is even. And then I'm going to say underneath, you do not have to write this, but it's just nice to see it. If n is an even number, it means that 2 goes into it. Even numbers are represented in the form 2 times k for any k. Every even number has a 2 as a factor. Okay, what's the other possibility?
N could be even or N is odd. Okay, quick check. If you imagine any even number in your head, how do you get to the next odd number? I think I heard, I think Rafa, did you say add 1? Do you guys agree that for any k, 2k is even, and for any k, 2k plus 1 winds up odd? All right, we have covered half the basis here. It's either an even degree or an odd degree. Okay, what about the leading coefficient? I don't want to specify into even and odd. How could you separate those? Ooh, say that again. Good. A sub n could be positive, or a sub n could be negative. Here's what I want you guys to do. I'm going to give you like 90 seconds, I think, with your calculators. I want you to test the simplest graph of one of them, pick a positive leading coefficient and an even, and a positive and an odd, and then pick a negative leading coefficient with an even and odd power. And I want you to graph them and compare them. There's a shortcut here to telling me exactly how my function ends. Do you guys understand what I'm saying? Give me a positive number. 4. Give me an even number. Cool. With 4x squared, could you graph it? Like, could you graph y equals 4x squared on your calculator? Do you know what it looks like? It's a parabola. Do you know which way it opens? Up and up. So we just said if it's positive and even, I'm going to give us much more formal language here in a second. But here's what I want to be real specific about. It goes up to the left and up to the right. Like if we do this with a parabola and then make it really obnoxious, it goes left and right. Because it does. It gets steeper. Do you guys agree that and try this, see if you can break it. If n is even and it's positive, it goes up to the left at the end and up to the right at the end. Try it with a couple more positives and other even numbers. So x to the 4th and 8th and 66th. I don't care what numbers you pick. Verify that this is what the end behavior looks like. Then change values of a and n to see what the other end behaviors look like. Cool. I'm going to give you a moment. I'm going to pause my screen briefly. Let's just check out what happens. I have, in this one, guaranteed, no matter what n I pick, this is always going to be even, right? So if I pick 1, it's 2 times 1 is 2. If I pick a 2 for n, it becomes to the 4th power, 6th power, and so forth. No matter what happens, ooh, that's weird. Why is it doing this? Oh, because it's letting me do it there. Time. We can't jump by decimals. N, step by 1 at a time. 1 at a time. Cool. All right, now we'll try it. If I do this, no matter what I do, what happens with the end behavior as I go left or right? Do they both go up? Now, if I require that they can be negative, and no matter what n is, do they both go down? Cool. We've learned half the math dance at this point. Up, up, or down, down. Now, beyond that, if I wanted instead to guarantee that I have an odd exponent, I'm going to make that plus 1 go to the right spot. This now why won't you do it? There we go. Here we go. 2n plus 1. This guarantees that no matter what n I pick, this is an odd number. So let's keep it positive. And we now have an odd exponent. What do you notice? As you go left, what does the function do? As I move further left, the function goes further down, right? And I'll zoom way out so we can see it. Is it still the case now? And now, and now, and now, and now, everywhere? So all of a sudden, it turns out it doesn't matter what we change into this. So if I say plus 4, and I got to think about this, x to the 2n minus 1, which just makes it the next power down, I bet we still see all the same stuff happening. So let me struggle with this for a second. Okay, this graph is a lot crazier, and it's kind of wild, but check it out. Does this thing, as I go further left, does it still look like it just goes down? As I work left, does this guy still just keep going downward? Okay, and this one's hard to tell because it's really steep. But as I go further right, what's it doing forever? It's going up. You guys can verify this with as many functions as you like. Quit it. pretty sure that we're all going to agree to this.
Now, where people get goofed up when you're drawing these is the arrow stuff. This is our leading coefficient test for end behavior, and we'll clarify this here in a second. What I want you to make really sure of is when we talk about end behavior, it says x goes all the way left and as x goes all the way right to both negative and positive infinity. Make sure that you have a slant indicating, I know that as I go left, it goes down in this situation, and I know that as I go to the right, the function goes up. It probably won't be that slanted when you actually see the graphs, but this will help to summarize it. Now, we have up, up, or down, down, up, down, or down, up. Those are the only four possibilities. You put these together, whatever combination you want, you get these sweet dance moves that we can all do at any dance that we might have. Is this really formal mathematics? Does it feel really formal to you guys? Maybe a little bit. Check it out.
I am A-okay with these pictures. Like, I use these all the time. I'm not going to make you write them, but I do want to focus. Let's do this one right here, because we're going to learn a little bit new notation, and I lied. I want you to write this down. On test quizzes and stuff, love this. The pictures are so easy to write down. However, I want to say and see mathematically what this actually says. So in this spot, I'm just going to say here, and we'll just drag it down so it's organized nicely. We have two situations. In this, if it's an odd power with a negative leading coefficient, as x goes which direction do you want to start with? So x can go either to positive or negative infinity. Let's start with negative. The formal notation here is as x approaches negative infinity,
we see something happening with the y values of my function.
As x approaches negative infinity here, what does f of x approach? Positive infinity. Now, what this is telling me, just like written here,
as you go really far left for your function, its values go really high up, which to me certainly looks like up and to the left. That's only half of my end behavior though, right? Because I have end behavior to the left side of it and I have end behavior to the right.
What would the right statement look like here? As x goes really far to the right, how do I write that using this notation? Really far to the left was negative infinity. What's really far to the right? Positive infinity. What did my function do in this particular case? And we can change the language, and sorry, that was terrible timing on my part, because I'm looking at people and I'm getting kind of glassy-eyed.
Let's just change it a little bit to feel just slightly less formal. As you pick further values to the right, the function goes which direction? Down. Like, we can see that happening.
Alternatively, if we make it a little bit more true, as x approaches infinity, f of x, my y values, approach what if they go down forever? Negative infinity. Could we do this statement for each of these four? Do we have to? I don't really want to. I'm cool with just this one if you are. Okay, last little thing that I will do is all of a sudden, I'm just going to put right here, this is telling us end behavior. Now, this can be misleading, but when we talk about end behavior, I'm just worried about after it's done changing and doing its crazy bendy curvy stuff, what happens as I go forever? The end behavior here. Okay, beyond that, I'm just going to do a really quick example. So, quick example, I want you to tell me or to state the end behavior, which I'm going to simplify as EB. And I'll put that over here. EB is what I'll use for end behavior. For each of the following functions, and this is going to go super quick, we don't need a calculator, we don't need anything other than this lovely table. Here we go. F of x equals negative 3x to the fourth plus x squared minus 1.
Can you tell me the end behavior with arrows? Now, in my mind, I always simplify this down because I don't know exactly what this graph looks like, but I do know the end behavior. What's the easiest even number you can think of? 2. Do we all agree that x squared is easy and it's either this with positive or this with negative? What's the easiest odd number you can think of? Okay, this is positive x from your perspective, I'm pretty sure. Is that right? Yeah. And this is negative x to the 1, right? If you can remember what x squared and just x do, you get all the rest of them for free as long as you can tell me if a number is even or odd. Okay, looking at this. Even or odd degree? Even. 4 is even. Okay, coefficient, positive or negative? So in your head, even if you don't have to check the table, can you tell me what a negative x squared graph looks like? It's down there, right? And I'm using squared because it's easier for me to think about that even number as a graph. Do you guys agree that if it's negative and even, down to the left and down to the right? Super challenging? Do we need to do another one? All right, well, let's keep hustling then. Okay, one of the parts that you told me, and JV, glad that you brought it up at the end because you are the person that said end behavior. Beyond that, do you guys remember any of the other things I asked you to identify that we might need? X-intercepts. I'm going to change that language just a skosh. But cool. We have leading coefficient test. Super valuable. Beyond the leading coefficient test, I'm going to switch to yellow now. We are going to have also a discussion, and this is going to be a repeat. We're going to talk about zeros of polynomial functions. Okay. We have 4 statements that I just want to make sure that we can get out of this. We're going to start with a little statement. Given the polynomial, and I'm just going to say the poly, f of x, we get the following statements. I'm going to leave with a little colon. Okay, all that we need is a polynomial. And we're going to talk about the zeros. Now, these equivalent statements, we've seen these before. First off, I'm just going to say that I didn't include it. We're working with a number, but I think it'll make sense here in a second. Step 1, we could say that some number x equals a is a 0. Sorry?
Is that an I after get?
1, I'm sorry.
Wait,
Get, colon.
Oh.
Although it does look like an I, that's my bad. We get 4 statements, and I've made you bring these up over and over, so they probably look familiar. X equals a can be a 0. Now, I like to jump immediately to the following. If x equals a is a 0 of this function f of x, then that also, same thing, means that x minus a is a what? Factor. Love it. Of the function f of x. Okay, we can find a 0 or the factor. These are interchangeable. Beyond this, we can keep going. We could say that instead of x equals a being a 0, we could say that x equals a is a solution. And I'm going to use my shorthand SOL apostrophe N. And specifically, when we talk about solutions, it's a solution of f of x set equal to what? 0. Good. Okay. Last one. We could say that this ordered pair, a comma 0, is a what? Or an what? One more time. Root. Or since we're talking about specifically an ordered pair, we'll say an x-intercept of f of x. And then I didn't include root. I probably should. There's 5 statements. X equals a is a root of f of x. These are all contextual depending on the situation that you're looking at. A 0 and a solution, the solution that you get from setting it equal to 0, the language, I hope, makes a clear connection there. All right. Beyond this, how do you find zeros? So if I give you a quadratic and said, hey, find me the x-intercepts, what F word immediately comes to mind? you factor. Okay, so I'm just going to make a note. Find zeros using factoring techniques. I'll say using factoring. Now, I know that we have a big factoring section coming up where we're probably going to expand on what you guys already know. Do you want to do a quick additional practice of factoring, or have we been factoring so frequently that we can hold on? Charles, how's your factoring? Do you need another example? Cool, let's do one. So one example that I want you guys to talk with one another, and I'll come around if anybody needs additional help. I want you to find me, and let's see here, find factors of, and here we go. On A, let's get real crazy. We're going to have a function, g of x, that is x cubed minus 12x squared plus 36x. I'm a posit. I want you guys to discuss or to signal that you need me to help. But think about your flow chart. I'll never take the flow chart back out. I always run 1, 2, 3 in my head. Those are my steps. I'll give you a second. We have found all the factors. Now, there's an immediate nice question here. Instead of asking for the factors, pretty common they're going to ask you for the roots or the solutions. Can you guys tell me the solutions? So this is going to feel weird, and we're going to think this out, and it's going to feel unnatural the first time we write it. Here's my factors, which is what we were asked to do. And I'm just going to put this here. If I asked instead for the solutions or the roots, can you tell me the values of x that make each one of these equal to 0? What, and this is such an odd question, what value of x makes this x equal to 0? 0. I hate that question, but I don't know a better way to word it. What value of x makes this factor equal to 0? 6, and this is going to feel odd. What value of x makes this factor equal to 0? 6. I want you to be redundant for a moment. We had that factor show up twice. Now, it turns out that there is something very specific about this situation. Do you agree that one of those zeros showed up one time? And the other one showed up how many times? Twice. I'm going to hop over to Desmos real quick. X cubed minus 12x squared plus 36x. X cubed, get out of here. Uh-oh. Somebody help. Minus 12x squared plus 36x. Okay. Now, I'm going to turn this one on, and we'll find a window that fits nicely, preferably so we can see everything. Here's our graph. Now, here's what I want us to notice. You guys found zeros, right? Specifically, there were 0 and 6. If I look at this graph, is that confirmed? Is the point 0, 0 on my graph? Okay, so it showed up once in our list. What does my graph do at that root? With respect to the axis, like, does it cross it or does it touch and turn? It crossed it, right? Now, that was the one that showed up one time. What was the root that showed up twice in that last example? 6. When it shows up twice, what does it do on my graph? It touches it, and then it turns around, right? Now, if I wanted to, and we can make a function, if I asked you to make me a function that has 4 roots, could you? If it has 4 roots, like you can, and you may not realize it yet, how many factors would it have? Our function, we found 3 roots. How many factors did we find? Here. Say that again, because we need to clear up the language here. Who thinks 2? I get it. I understand why you would think 2. Does everybody else agree why you'd say 2? However, when we actually list them all out, how many do we have to write? 3. So I get it, because you want to say that these are the same, but I want to really emphasize that they're showing up. So if I wanted one that had, I don't know, let's say it has x show up 3 times. That's my factor form, x times x times x. And then let's give myself an x plus 1. And if I raise it to the 4th power, can you tell me how many times that root showed up? What if I do it like this? Gross. Is that the same as x plus 1 to the 4th? How many times did this root show up? 4. So I'm going to kick back and I'm just going to use that nicer notation. And we're going to change the number so we can see if we can't make an observation here. So I'm going to actually make this x plus 5 so we can see it. Okay, so here's my graph. It's x cubed times x plus 5 to the 4th. And I'm going to write it in that nicer fashion. It's ugly when we just write it. I'm okay with it. Can you guys tell me the zeros of this function without looking at the graph? Here's the factored form. What values of x make it 0? So it's 0 and negative 5, right? Those are the two values that do it. I'm okay if you write it, but here's what I want you to think about. It's actually 0, 0, 0 thrice, and negative 5, negative 5, negative 5, negative 5 4 times. Do you guys agree with that, although it's just ugly to write it all out? So let's see what happens. When it crosses 3 times, an odd number, when it has 3 roots, let's see what that does to the graph. At 0, if we zoom way in here, what do? Do I touch and turn around, or do I actually cross? Ooh, maybe not certain. Is it because it gets kind of levelly? But check it out. If I just follow along, negative, 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 until I get there, and then positive, 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 positive. What did I do? Did I cross it, or did I touch it and turn back around? I crossed it. When it showed up 3 times, it crossed. Or in the previous example, when I showed up once, it crossed, right? Let's look at this one. How many times does this 0 show up? Or negative 5? Shows up 4 times, which is fundamentally different than the number 3. So we'll go over here. What happens when it shows up that number of times? Does it cross, or does it touch and turn at the root that shows up 4 times? It touched and turned back around, right? So if it was negative, it's negative on both sides of it. If it was positive, it's positive on both sides of it. It turns out, this idea, do you guys agree that, like, when we look at it, that seems to be what's happening? Okay. Moving on from here, then, we get a new lovely word that you've likely never heard before. Except for today. All right. That whole idea that we've just been talking about is this idea of, it's a definition that we're just going to sneak in within our zeros. Here's our definition. Multiplicity. Okay. This is an idea that I guarantee if you wind up taking calculus, no matter who it's with, at the school or not, doesn't matter, multiplicity will show up again, because knowing this and keeping this locked in and ready to go saves so much work in a huge variety of problems. Anything beyond pre-calc, and even later this year, this is going to be valuable. So multiplicity, we're going to say that this is simply the number of times a root repeats itself. And I'm just going to stop at repeats. The number of times a root repeats. So on the example that we did just a second ago, we had 0 and negative 6 were the 2 roots that we came up with. Was it negative 6 or was positive 6? I'm sorry. What was the multiplicity of 0 in that problem? How many times did it show up? So look at the example in our notes, not the one that we did on the board, I'm sorry. Once. It had a multiplicity of 1. How about the plus 6? So its multiplicity was 2, and they did fundamentally different things. Just like we saw 3 and 4 do fundamentally different things on our graph. While we're looking at this then, we're going to make the following big important statement. A factor, which we're going to say is just going to have the form x minus a. And we're going to leave the possibility that it shows up more than once with the power of k. Okay, a factor x minus a to the k, where we're just going to specify that k has to be greater than or equal to 1, has multiplicity of k. Has a multiplicity equal to k. Now, the number of times the factor, the root, the solution, whatever you want to word it, the number of times it shows up in your list, and it's why I made you repeat them, is your multiplicity. Now, there's only two possibilities. It can either be an even multiplicity or an odd multiplicity. So, two big statements. If k is odd, the graph, what did it do? It crosses. Or, and I'm going to write crosses, but we have other language. Crosses the x-axis. Now, if we want it to be wordier, there's two ways that it can cross. It can go from being a negative to a positive, or it can go from being a positive to a negative. Those are the only two options. It crosses completely over. The alternative is that if k is even, what does the graph do? It touches the x-axis, and then does what? Turns, and I'm going to say specifically turns around. Okay. With just this information that we've seen today, we can now get sketches of functions that legitimately 40 minutes ago I don't think you would have been able to do. Let's do one together. We're going to sketch a function and see how close we are. Okay. Multiplicity, I promise it shows up a ton when we're dealing with inequalities and stuff, because when you need to decide if it's positive or negative and so forth, this is the easy way. If you find the roots, you know when it changed. Okay, let's do an example where we put it all together. And I'm just going to get rid of that. So no calculators allowed here, just so you guys know. We're going to sketch. Now, the idea of sketching is going to get more or less specific. We don't need to actually do calculations and stuff, and you're going to see why. So here we go. On example A, I want us to sketch the following. I want us together, without ever checking the computer, to graph x cubed minus 2x squared. Immediately. All right. We have talked about three things today. Can you guys tell me the order or the degree of this function? It's a third degree, right? Can you tell me if the leading coefficient is positive or negative? Okay, so imagine an easier than a third degree, because that's ugly. Show me with your hands y equals positive 1 x to the first power. Just x. Show me what that graph looks like. Show me just with your hand, with your arms, however you want to do it. Show me what y equals x looks like. Positive 1x to the first power. We all agree it's like this, right? Somewhere in there. I was trying to dab and make it awkward. In your head, the graph of x, it's actually this way from your perspective. That's my bad. Down to the left, up to the right. Do you guys agree? You could check your table to verify that, but a positive and odd does do this. So check it out. If we're trying to graph this thing, M behavior is going to be super helpful. M behavior. Down to the left, make sure it's down and to the left, up and to the right. Okay, what else have we talked about today? End behavior. And I think that was, for a brief second you stepped out. That table that we did earlier, Huggins, I had written end behavior EB right next to it. Leading coefficient test for end behavior. Okay, we talked about end behavior and then we talked about the zeros, right? Okay, so I'm going to do some scratch work on the side. Let's find our zeros. If I'm trying to make the zeros to this, I'm going to do two things. I'm going to set it equal to 0. And then we're going to do what first when we're trying to factor? GCF. What goes into both of them? X squared. And it leaves behind an x minus 2. And I'm just setting it equal to 0 and doing the factoring, the GCF, and the plugging in for 0 part. How many roots did we just find? We found 3 of them. What are my 2 zeros? One of them is 0, and one of them is... So I'm not going to write it twice, and we'll see why. I love it. If you want to, please do. 0, 0, and 2. I will typically do this, and then I'm just going to make a little note. What was the multiplicity here? That was 2. And the multiplicity here? Why am I making this comment? Because maybe instead of just writing this, can you tell me what a multiplicity of 2 is going to do? Touch and turn. Okay, multiplicity of 1 is going to cross. If we have this information, does it seem like it's really enough to get a good graph? I bet we're pretty stinking close. And it doesn't really seem like it yet, but let's just try this. If we're making this graph, I really hate this stopping point. I want you guys to sketch this. Using only the information we have, you're going to have to get a couple values out of it, but don't plot more than I wouldn't do more than 3 points. Cool. Your job tonight is to use this information, no calculator, try to graph it. Cool. We'll pick up right here tomorrow.